Hi, I'm Uli. I'm one of the researchers involved in the EXO Catlin ZView survey. My team is testing whether we can use Catlin images to learn about fish abundance and diversity across the many kilometers of reef photographed. With your help, we can establish the EXO Catlin ZView survey as a tool for assessing fish populations. By extracting information from the Catlin imagery, we can learn a lot about fish populations around coral reefs on a global scale. We've got hundreds of thousands of photos to gather data from, and we see this as a great opportunity to involve Tropics 101X students in real data collection, often called a citizen science project. Being part of a brand new project which relies on custom-made data processing software and novel technology means that we also value your feedback on any glitches and/or ways you think we can improve the project. Let me explain how our project works, what we've accomplished so far and what we want to achieve in the future. First of all, why is my team focusing on fish? Well, fish are important to people commercially and as a source of food. Data about fish diversity and abundance is very useful, both to protect our resources through fishery management and also for understanding the ecology of reef systems. So far, the Catlin imagery has been used for the assessment of benthic organisms, so there's a great opportunity for us to extend this to include fish data. The first step in setting up this project was to gather some data on site. These data are used for what we call ground truthing. Professor Finn and Dr. Rolfsema talked about using this technique in lecture 6.3 to make sure the interpretation of their satellite measurements was accurate. Similarly, we surveyed in the Maldives with both the Catlin ZView survey and traditional diver methods to count the fish along the same transit lines. Later, we can compare the results from our images to our scuba diving results for each site to see how well they correspond. We visited over 20 sites that you can see on the y-axis here, and we counted all of the fish that we saw along 3 50-meter transects at each site. It was a lot of work. We counted over 22,000 fish in 2 weeks of diving. So now we know what species of fish were present at each location and how abundant and big the fish were. It's important to have these data so that we can check that our results from the photos are accurate, or to see how the results between the two methods might differ. Once we collected those data, it was time for the computer lab. We had to develop software that would allow us to label and identify fish in the images. But there are hundreds of thousands of images, so it seems it would be a very valuable investment of our time to train a computer to find and possibly even identify fish. Through collaboration with Professor Franz's laboratory at the Institute of Optical Systems in Konstanz, Germany, we started to develop a fish labeling tool soon after the field trip. Instrumental for the success of this project was Michael Grunwald, a PhD student in the Franz laboratory. Michael and I worked out the functionality of the system while a team of students in Germany developed the software under Michael's leadership. The time difference actually helped the project along since it was being worked on 24 hours a day. So this is the expert mode of the fish labeling tool. You can see these green boxes, and each of these boxes has a fish inside it. So someone's gone and labeled many fish in this image, and here you can see all the names, all the species names that we've assigned to these fish. We had the original label tool that you just saw designed for us researchers, but the going was slow with only 3 people labeling fish. So we thought, let's simplify this a bit so that anyone who's interested can get involved and help us out on this really neat project. We partnered with Tropics 101X to build our software into your edX course. Even if you've never had experience with Fish ID, you should easily be able to pick it up. We also put together an instructional video about the platform. I would really encourage you to watch that video before participating. It should explain everything you need to know in order to use the Fish ID program. We've actually used this tool in an older version of Tropics 101X, where the students only had 3 weeks to complete the final project, and we already got some pretty awesome data from that. In the rest of this video, I'll walk you through the results of that, and I'll explain how we're using those results to improve our machine's Fish ID skills. The more data your students can give us, the better our machine will get. And we feel it's also a valuable experience for you to be a part of some real science in action. As you can see here, Tropics 101X students identified over twice as many fish as the 3 experts on the project could. and they did it in half the amount of time. They didn't identify fish down to the species level like we did, but they were very good at finding the fish with high accuracy, which is extremely helpful with the first step of our machine learning, finding fish. Automating the identification of fish down to the family or possibly even species level is our ultimate goal, but we're not quite there yet. For the fish detection, we need several thousand examples of fish. For the family or species identification, we also need several thousand examples for each category. So you can see that this requires a lot more data, and it would be wonderful if you could have a go at identifying as many fish as you can at the family level. So how do we get a computer to recognize fish? Well, each fish you have selected is extracted and used as an input image, also called patch. All patches from all observers go through various stages of normalization before a feature detection algorithm, often used for the detection of humans in images, is applied to each patch. The resulting images are then used to train the computer until it can recognize all fish in the training set. The exciting step is then to test the computer on images it has never seen before. Here's what the fish look like from the computer's point of view. Here you can see how uniformly colored fish, such as this triggerfish or this eagle ray, show up really well against a uniformly colored background. So you can see the outline here, you can see its shape really well. You can also see that this uniformly colored fish shows up really nicely against a non-uniform background. It gets more interesting when you have a patterned fish, so a non-uniformly colored fish seen against a non-uniformly colored background. It makes it much harder for the machine to pick it up. I guess this is the principle of camouflage demonstrated here. As mentioned before, we need to test the machine to see how well it has learned the task of finding fish. So we train the machine on only part of the data. Then we optimize all the parameters possible until the machine can pull out the fish reliably. Then we test whether the computer can also recognize the fish in the images it has never seen before. When we did this with our combined data, we achieved 100% accuracy for the training set and 95% accuracy for the novel images. This is very exciting as it shows that we can use machine learning to find fish in the XL-Catlin Seaview survey imagery. Here you can see what the computer found. The red boxes here indicate the position of fish the computer found when it looked at the same images but at different stages of the process. And then the blue boxes, and you can see there's only one blue box per fish, indicate the final decision the computer has made by combining the results it found in the red boxes all together into one result. And you can see that the computer even managed to find this dark fish seen against the dark background, or this fish which almost looks like a coral. So it did its job really well. So the next step is now to include more parameters to see if we can further improve the accuracy, and also to see if we can identify the species or families of each fish. We need your help to get more labeled images for each family class and more detail on species from fish experts, and then we can train the machine to identify fish. We'll do this in two different ways using two different machine vision approaches. The support vector machines we've used so far, and then a novel approach using neural network methodology. In a project like this, there are a lot of people involved. Instrumental were particularly Maria Berger, the Professor Franz Laboratory, my expert labelers, and of course the XL-Catlin Seaview survey team. And thank you to anyone who chooses to participate in Task 2, Option 2 of the final project. It might be a bit trickier than other parts of the course, and unfortunately we can't give you as much feedback or transparent grading that we know many students like to have. But this is real data collection. In science, we simply don't get to know if our answers are right or wrong. We just have to do our best and see what the results tell us. So I encourage you to try it out. And I'm excited for all the possible questions we can answer using the data your work will provide.